My name is Marco Castronuovo. I come from Italy. I work for the Italian Space Agency in the Deep Space Observation and Exploration Unit. Today I will talk about orbits and their properties, so orbital dynamics. So the vis-viva equation may be rewritten computing the velocity from this equation, and we see that the velocity is, as I said before, is not a constant along the orbit. It depends, in fact, from time to time by the value of r. Of course, when r is a minimum, the velocity is maximum, and vice versa. In case of energy equals to zero, we have what is called the parabolic velocity, or velocity of escape. So this is the minimum velocity necessary to escape gravitational force, gravitational field produced by a central body. And this is given by, as you can see, the square root of 2 times mu over r. A satellite that is launched with this velocity in any direction will not return to the central body. Of course, this assumes there are no other forces acting on it. Also, when the radius is equals to a semi-major axis, so it means the orbit is circular, we have always the same distance from the central body, we can obtain the circular velocity. This means that for any given distance from the central mass, we have a specific velocity. We can now see in this table the circular velocity and escape velocity for some celestial bodies. You can see, for example, for the Earth, considering the equatorial radius 6,378 kilometers, a circular velocity at that height is 7.9 kilometers per second. So this is the velocity that a body should have to circle the Earth at the sea level. Of course, this doesn't take into account the presence of atmosphere and so on. The period corresponding to this orbit at a height of 0 kilometers is 84 minutes. So this means that for any other orbit we will have a slower velocity, and we will have a larger circular period. So all periods of satellites around the Earth will be greater than 90 minutes. The escape velocity is 11.1 kilometers per second. You can see, for example, the Moon, which has a much lower mass and a smaller radius, has circular velocities of 1.7 kilometers per second, and periods that are from much larger than 100 minutes. To describe conveniently an orbit, a set of classical elements can be used. These are called Keplerian elements. They can be applied not only to Keplerian orbits, but also to real orbits, and later on I will explain how this happens. As I said before, Keplerian orbits are a simplification, are an ideal case that has some assumptions on the base. The orbit's size and shape can be determined by 2 parameters. To define the orientation of the orbit plane in space, we need 2 more parameters. that will be two angles, and the orientation of the semi-major axis within the orbital plane is given by a further parameter. And finally, the position of the satellite on the orbit requires the last parameter, the sixth parameter. For elliptical orbits, just a little bit of nomenclature. The perifocus is the point of the orbit where the satellite is the closest to the central mass. The periapsis, or perifocal distance, is the distance between the center of mass and the perifocus, and this is equal to the semi-major axis times 1 minus the eccentricity. Perihelion and perifocal distance are measured from the center of mass, but the perigee height is measured from the surface of the Earth. The most distant point from the primary instead is called the apofocus, and the apoapsis, or apofocus distance, is given by the expression semi-major axis times 1 plus eccentricity. So, of course, to obtain the perigee heights and apogee heights from the apoapsis or periapsis, you have to add or subtract the radius of the Earth. You can see the relation between the semi-major axis and these quantities. To define the orientation of the orbit in space, as I said, we need two angles. The first one is the inclination. The inclination is the angle between the orbit plane and the reference plane, and most commonly used reference plane is the equatorial plane. So, as you can see in this sketch, the angle between these two planes, I, the inclination, is varying between 0 and 180 degrees. Of course, for angles greater than 180 degrees, we will have an orbit that is rotating in the opposite side. When the inclination is between 0 and 90, we have a prograde orbit. When the inclination is between 90 degrees and 180, we have a retrograde orbit. Now, the intersection between the orbit plane and the equatorial plane is given by what is called the line of nodes. For an Earth satellite, the ascending node is the point where its orbit, the orbit of the satellite crosses the equator going from south to north, while the descending node is the opposite, where the satellite crosses the equator going from north to south. So, as I said, we need also to define the orientation of the line of nodes around the equator, to define the orientation of the orbital plane in space. And this is given by the parameter that is called right ascension of the ascending node, capital omega, which is often referred, especially in computer codes, as RAAN. And this is, as I said, the angle between the vernal equinox and the ascending node of the orbit. The vernal equinox is the reference direction of the Earth-centered reference frame, which aims at the vernal point, also in the direction of the Aries constellation. This is also why it is called Aries point, and is often symbolized by the gamma Greek letter that is the symbol of the Aries constellation. So once you have specified the orientation of the orbit plane, we need to specify the rotational orientation of the major axis, the line of axis, within that plane. This is done defining the argument of perigee with small omega, which is the angle measured in the orbital plane in the direction of the satellite motion from the ascending node to the perigee. And finally, we need to specify where the satellite is on its orbit, and this is done, for example, by the true anomaly, that is the angle measured between the perigee and the satellite position. So this, of course, is varying between 0 and 360 degrees. So to summarize the orbit geometry in space, we have for circular orbit and elliptic orbit these parameters. Semi-major axis for the circular orbit, of course, is equal to the radius, is always constant. The eccentricity is 0, and we have always pericenter and apocenter are the same, since we have always the same distance. The velocity is constant along the orbit, is given by the square root of mu over r. And we have, of course, a negative energy, total energy per unit mass. And we have a constant mean angular motion given by the square root of mu over cube of r. For the ellipse, instead we have semi-major axis, of course, is the mean distance, but we have an eccentricity that is not 0, so we have a perifocal distance, small q, and an apofocal distance, capital Q. And we have a varying velocity along the orbit, as we saw. We still have negative energy, and we have practically the same expression from the mean angular motion, where we have semi-major axis instead of the radius. So summarizing the Keplerian parameters, we have orbital plane positioning is given by rad ascension of ascending node, capital omega, and inclination of the orbital plane. Orbit positioning in the orbital plane is the argument of perigee, which gives the orientation of the line of axis on the orbital plane. The shape of the orbit is given by two parameters, semi-major axis and eccentricity. And the position of the satellite on the orbit is given by the true anomaly. So we need 6 parameters to define the orbit. As I said at the beginning, this can be alternatively described by the other 6 parameters, for example, the state vector with 3 components of position and 3 components of velocity. And here in the bottom we have an expression also giving the value of the radius as a function of the true anomaly. You see, this P is called also parameter, is as an easy expression in terms of semi-major axis and eccentricity. And now we can see a small animation that will give an idea of these parameters for an orbit. So we see here satellite orbiting around the Earth. These 2 vectors are the periapsis and the apoapsis. And you can see that the plane of the orbit is given by, can be expressed by this inclination. This is the angle between the orbital plane and, in this case, the reference plane is the equatorial plane. And the line of interception between the orbital plane and the equatorial plane is the line of nodes, exactly this one you can see here.